Good evening, everyone. This is our second tea time of the year, 1 week after the first tea time. Last week, we talked about a very recent college graduate who was working on the business side of the sciences, doing pharma stuff at a therapeutics, Sage Therapeutics. This time, we're going to go to the opposite end of the spectrum and go deep with a research scientist. So this is Dr. Blase Billack, who is a professor of pharmaceutical sciences at St. John's University in New York. He has his bachelor's degree from the University of Richmond. Would you consider that a small liberal arts college?
Absolutely.
Yeah, I kind of always considered it that too. I went to Swarthmore. I kind of consider them in the same kind of.
Yes.
Rutgers University for his Ph.D. and then the Medical College at Cornell for his postdoctoral fellowship in molecular oncology. So in chemistry, pharmacology, and toxicology, and then molecular oncology. So thank you very much for coming. We're looking forward to it. And these guys tend to have a lot of good questions.
Well, fantastic. Thanks for inviting me, Dr. Ciarleglio. Hello, everyone, and it's an honor to be here. I also graduated from a Catholic high school. I went to DePaul High School in Wayne. I know. Please stay logged on. Probably it's your competitor in sports and everything. But it really was a great experience for me, and I learned a lot of good things, made some good friends, and kind of helped with the first step. So when I talked to Dr. Ciarleglio about titles, it's kind of a long road to get to professor, but maybe you'd want to know about the road. And there's also many diversion points that you can exit the road and enter some cool careers as well. So I'm going to talk to you a little bit about how I became a professor and life as a research scientist in academia. And so my story starts in 1991. Most of you were probably like minus 20. I don't know. But I was a senior in high school, and I had applied to the University of Richmond. And I went to visit a few schools during my senior year with my dad. He was down in Virginia for a business trip, and we went to a few places, and one of them was University of Richmond. So in August of 1991, I made the trip down from Wayne, New Jersey, where I'm originally from, down to Richmond. As you can see, it's almost a 6-hour drive. Literally, my mother was crying because I had never really been away from home for more than a little while.
Yeah.
So there we are driving down to Richmond, and it was pretty cool. And I get there, and it's a very beautiful place to study. And I studied a lot. I was lucky. I didn't have to work during the academic year. I worked in the summers. And I got involved with my classes, and I was spending many hours a day in the library and that kind of thing. And it was a great place to learn. And during my sophomore year, I took a class with a professor named Dr. Kinsley. And Dr. Kinsley taught psychology, and I was taking some elective classes. I wasn't really sure what I wanted to do. And at Richmond, you have to take some what's called core classes before you actually declare your major. And so I took a class with Professor Kinsley, and it was in psychology, and he was very interested in behavior. Why do people behave certain ways? And when he started lecturing, I almost got hypnotized. I was really fascinated by the topic, and I was interested in it. It hadn't been something I had thought much about. And at the end of the semester, he just made a general request to the class to ask if anyone would be interested in doing research in his lab. And after the class was over, I walked up to him and I said, I think it would be interesting to work in your lab. And so he invited me up to the lab, and I met his graduate students, and he showed me around, and he had rats in his lab, and he did behavioral studies where he injected certain types of drugs into the brain and looked to see how the behavior, certain well-defined behaviors would change. And so I was really into it, and I agreed to do research. And so during my sophomore year, there I was. And the first assignment I got was to change the rat cages. And let me tell you, it wasn't really fun because it was smelly and I was kind of scared of the rats, and it wasn't really fun. But there I was. I had said I would do it, so I kept my word. And every week I came in and I changed the rat cages, and nothing else happened. Like, he didn't come in the lab to show me anything. His students didn't really talk to me. And it was kind of like somewhat not what I thought it would be. And so here it was now December. I had done this all semester, and I was ready to tell Dr. Kinsley that I think this isn't what I want to do. I'm going to quit. And he comes into the lab and he says, "So are you ready to start doing research?" And I looked at him and I said, "Why did you make me wait the whole semester? I mean, it's not so fun changing the cages." And he said, "Blase, I needed to know that I could trust you because we work with controlled substances in this lab, and I just can't let anybody work in this lab and work with heroin and cocaine and so on." And I'm sharing that story with you because, a lot of people looked at me during this time and said, "You're crazy. You're just like changing rat cages. Get out of there, man. Come out with us. Let's have fun, whatever." And so I don't know if you got anything out of that story, but it was an interesting experience. And of course, I did it as a volunteer. I didn't get paid for this. But look at the investment, right? So I spent that time, and I eventually was able to go to graduate school. I didn't have to pay. I got a fellowship, and the rest is history. So the story I'm telling you is Dr. Kinsley, gave me a purpose. I was kind of a kid that was good at many things, but I didn't really have a purpose. I didn't really know what I wanted to do. I was just kind of going with the flow because, had to do something. And so my first point to the audience is find a purpose. And in college, it's a great time to find that purpose. So take various classes and see what you like, see what you're good at. And then find a mentor. And really, Dr. Kinsley became my mentor. And a mentor is somebody who shows you the direction to go in to reach your goals. And so it was an amazing relationship. I worked for him my sophomore, my junior, my senior year, and eventually he wrote my reference letter that got me into Rutgers, which I got in on a full scholarship. And so my mentor helped me very much, and I miss him. He passed away a few years ago prematurely, and I'm eternally grateful to him. And so then my next stop was Rutgers University, back to New Jersey. So for whatever reason, I decided to come back home. Virginia was great, but I guess it was just a little too far from home. And I got into Rutgers. I got into a toxicology program. I became interested in how chemicals affect the body and how chemicals cause toxic effects on the body, from doing research with Dr. Kinsley. And so at Rutgers, I got into a Ph.D. program in toxicology. And this is the building I spent 6 years of my life in, called the Environmental and Occupational Health Sciences Institute. And for those of you who are looking at Rutgers, maybe right now as a potential college, this is located on the Bush campus, which is in Piscataway, not too far from the main campus, the College Ave campus, but this is the Bush campus. And here we have a lot of the science at Rutgers, although not all, because there's also some on the Cook campus as well. And so at Rutgers, I got involved in doing research in toxicology. And in particular, I studied how chemicals can affect your immune response. And of course, I didn't really work with people, but I worked with cells, with tissues, and we tried to understand how certain chemicals can affect your immune system. Now, again, you're getting to the end of high school where you're going to now be thinking about, is college for me? Should I go? I would certainly recommend it, even if you end up going into a different kind of profession when you're older, trade or something. I think a nice liberal arts background gives you a lot of different exposures and opens your mind to lots of different things. We could certainly talk about it later. But in order to get your PhD, you obviously have to have a bachelor's degree. So you have to finish a 4-year college degree, and then you go for your PhD. And in order to get your PhD, you need to take more classes, you need to pass a few big exams, and you need to discover something new. And so the PhD, by the way, is considered the highest degree in every country of the world. So if you get your PhD in America and you decide that you want to go live in Australia, you don't have to take any extra classes in Australia. You are the top. It's called the terminal degree. And so it's not easy to get, but it's certainly achievable if you are persistent and if you work hard and if you're interested in what you're working on. You can't really look at it as how many hours you spend in the lab, because during my 6 years at Rutgers, I published 4 manuscripts. I discovered a few new things. Some of them are not earth-shattering. So, for example, we discovered that a certain bacterial component can activate responses in your liver. And other people had at that time demonstrated that it can activate those similar responses in blood vessels. So it's not necessarily shockingly new, but in order to defend your thesis, you have to find something new. Okay. So it's a long road. I don't want to, lie about it and make you think like it's so easy. But it's fun. I mean, you're doing experiments. You're at the periphery of new knowledge. It's cool. But you have to kind of be patient, I think. If you're expecting instant return on invested time, you'll be frustrated. After I finished my PhD, I went and did something called a postdoctoral fellowship, and I did that in breast cancer research. It was a different field from what I studied for my PhD, which was more of immunotoxicology. This was an amazing time, right? So I get this job to do research at the Weill Medical College of Cornell. There it is. It's on York Avenue, if you know Manhattan, in between 68th and 71st Street. It's like in the prime site of Manhattan. I started on September 1st, 2001, and you know what happened just 10 short days later. So it was very, I'll never forget it. It was a terrible start, but it ultimately ended up being an amazing journey. I worked for a professor who studied something called the BRCA gene, the BRCA1 gene. He taught me how to make mutants of the gene, how to test those mutants in yeast cells and in kidney cells, and it was just amazing. So let me pause here, right? So here I am after 4 years of bachelor's and 6 years of PhD, and I get this $30,000 a year postdoc, right? So you heard me right. Postdocs don't make a lot of money, but I didn't have anything to stop me from doing it because, I didn't have a family and I didn't have huge expenses. And so I said, I want to go work for these people because they are so smart and interesting, and I'm going to get better just by being around them and learning from them. And like I said, maybe I didn't make a lot of money, but I didn't have a lot of debt because PhD can be basically funded for free if you match yourself to the right program and you get a fellowship or sometimes something called a teaching assistantship. And so I got to tell you, those 2 years were probably intellectually the richest of my life. And I met so many cool people and smart people. And I realized, oh, my God, I thought I was so smart. And then there you are with people who, in terms of intellect, are very, very smart. So it's to make you a better place. However, I didn't stay there forever. There are people who get trapped into the postdoc life and they end up being postdocs for 6, 7, 8, 10 years. After 2 years, I started looking for a professor job because Dr. Kinsley, my mentor from Richmond, had kind of showed me how cool it is to be a professor. You can work with students, you can do research, you can teach. Your lifestyle is in my opinion, is the kind that would suit my personality well. And so to become a college professor after your PhD, you need to specialize. And so I specialized in doing some molecular pharmacology and some molecular oncology research. And it's not just enough to work in the lab and be with the smart people, but you also have to discover new things because your mentor is paying you. And you need to publish those things so that you can show others that you are capable. So there is a certain element of stress. I don't want you to make it seem like there's no stress. But if you're working a lot, if you're alongside ambitious people who are excited and enthusiastic about what they're working on, there's so much cool stuff going on now. Like, for example, maybe, there's this movement to try to get away from animal work in the lab. And of course, I do a lot of animal work in the lab. But people are making these 3D tissue culture models where they're trying to make an artificial heart, that beats, or an artificial liver that beats, that metabolizes drugs. It's like a really cool time to be in research. Okay, so anyway, after Cornell, I came to St. John's as a new assistant professor. And so usually the first step in the academic world is assistant professor. I mean, you're basically a professor, but the title you have is called assistant professor. If you look right in the middle of this slide, you'll see the library in the distance. And that the lawn in front of it is referred to on St. John's campus as the Great Lawn. So you might think, oh, St. John's is in Queens and it would have an urban feel to it. But in fact, we have a very nice campus. It's very pretty, and it's an old golf course that they converted into this university back in the 1940s and 50s. And really, it's very lovely. You can take a stroll. It's safe. You can drive back home in an hour and a half. It's kind of like the best of both worlds. And if you look at that middle picture, you'll see the Celtic cross. There's a bench there. A lot of people sometimes sit there on a summer day for lunch, and a lot of students play Frisbee out there on the Great Lawn. And then obviously in May, this is where we have our commencement ceremony, and all the proud parents are standing on the lawn, clapping for their kids as they receive their diplomas. So it's a nice place to be. And so on the left, that's the path to the College of Pharmacy and Health Sciences where I work. And on the right is just another path to the library. All roads lead to the library, Okay. So just to review maybe some of the things I hope you would take from my journey and maybe think about is find a purpose, find a mentor, and realize that mentor is going to help you, and that mentor is going to point you in the right direction. Now, to get your PhD, you're going to have your bachelor's first, and then you're going to need to take classes, pass a few big exams, and discover something new. And to become a college professor after your PhD, you're going to need to specialize. And you're probably going to do that through postdoctoral research, where you're discovering new things and publishing your research. Now, once you've done that, keep going. Be a mentor. Help people reach their goals. And to become a tenured professor, it never ends, I'm going to be honest. It never ends. Like, if you think about the whole process as, oh my goodness, it takes so many years and this is not for me, don't think about it that way. Just take it one day at a time. Because the truth is, you only have today. That's the only guarantee you got, is you have today. Every new day is a gift. And you can think about years down the road, and you could fuss about it. But if you take it one day at a time, it becomes a little easier, and the journey is not as hard. And so, here you are, you're assistant professor, and then you're on the clock. And the clock is called the tenure clock, and you've got 5 years to get tenure. And in order to get tenure, you have to prove to your university, whether it's St. John's or Seton Hall or University of Cincinnati or whatever, you have to prove to them that you're good at teaching, that you're good at research, and that you're willing to help the university when it asks you to. And what does that mean, willing to help the university when it asks you to? Well, maybe the university needs you to serve on a committee. You know how like at high school you have something called middle states, and middle states looks at your curriculum and they say, oh, you have a good curriculum, but it would be a little better if you improved here and if you did this and da-da-da. It's the same thing at colleges and universities, and sometimes the university needs faculty input to improve itself. And sometimes those committees take up a lot of time. But still, you still get your summers off. You don't have to work in the summer. Most of us do because we're crazy, but you don't have to, right? Usually your summers are yours. But like I said, since we have to do research, summer's a nice time to do it because you don't have to teach as much. And so we do our research. So in order to get tenure, there are 3 things: teaching, research, and service. And of course, you need to publish. Now, I know I'm going a little bit long. I'm just going to give you a little overview of my research, like what can you do in an academic setting. So my research is called academic research because it happens at a college or a university. Just realize when you have your PhD, there are different roads you can go down. So there is also something called industry. You could go work for Pfizer and make a vaccine, right? You could go work for Merck. You could go work for Johnson & Johnson. There's plenty of opportunities for researchers in industry. There's plenty of opportunities for researchers in government. So we have a lot of government agencies that, are actively always looking for new PhDs. Things like the Food and Drug Administration, things like the CDC, all the things you hear about in the news. And it would be nice to, have input from people who have the most recent knowledge in certain areas. But then there are other areas you can go in. A lot of nonprofits, the American Heart Association, the American Diabetes Association. They're always looking for science experts. There are startup companies. There are medical education companies. There's all kinds of things you can do with your PhD beyond just academia. But I'll talk to you about academia because it's what I know best. So one of the things you have to do when you become a professor is develop a research program. And the committee that's going to assess you for tenure is looking to see if you are a real deal researcher, meaning that you've come and you've set up a new research program and nobody's really telling you what to do. You're not working for your old mentor. You're not rehashing things that you've done in the past, but rather you're starting a new research program that's completely yours. And so when I got to St. John's, it was 2003. We had just gone through the World Trade Center attack. And I sat down one day just thinking about what could I do my research on that would be kind of unique and new and not connected to things I've done in the past directly. And then I came up with the idea of chemical warfare agents. The World Trade Center was a terrorist attack. And about 6 or 7 years earlier, there was a chemical warfare attack on the subway in Tokyo, Japan. That was also in my mind. And I thought, it'd be nice if we had antidotes to some of these nasty things that are out there. And one of the nasty things that's out there is called sulfur mustard. We sometimes call it mustard gas. And sulfur mustard is designated by the military with the 2 letters here on the right, HD. HD. The D stands for distilled. And the H stands for the German word Harnstoff. Now, the German word Harnstoff, when you translate it into English, means hot stuff. Hot stuff. Sulfur mustard, from the very first time it was used in World War I, it was called hot stuff by the Germans who used it first. And the letter H was painted onto the canisters that contained it, so the soldiers knew to be careful when they were handling it. Later, they learned how to distill it and make it even more pure, so it became known as HD. So again, this hot stuff, this mustard, had burning properties, blistering properties, and can injure the skin, the eyes, the respiratory tract. And in World War I, this is the introduction of modern chemical warfare. World War I, the use of things like sulfur mustards, as well as another blistering agent called lewisite. And what makes this thing terrible is that there's no antidote to it. Even though it's been over 100 years since it was first used on the battlefield, we have really no way to kind of reverse the damage caused by mustards. So I thought maybe I could do some research in this area. And even now, even though there's a chemical weapons convention that almost all the countries of the world have signed, there's still a few countries that maintain large stockpiles of this stuff. So if you look on this picture, these are some old pictures from old textbooks looking at mustard injury. On the left, you can see a soldier. His whole back has basically been scarred by mustard exposure. If you look on the right, you see the soldiers in a trench. They're wearing gloves. They're wearing long sleeve clothing. They're wearing what we now call gas masks. And the reason for that is that in World War I, this style of warfare was used called trench warfare, where the soldiers kind of hid below the surface of the ground. They would pop their heads up and shoot their rifles, and they'd try to kind of beat the other army in the other trench somewhere on the other side of the field. But when mustards came out, what made them so terrible was that they're denser than air. And so, in fact, we call it a gas, but it's really not a gas. It's a liquid that gets dispersed, and it forms little liquid droplets that we call aerosols. And those little liquid droplets can be inhaled. They can get into your eyes. They can get on your skin. They can cause burns. And when they would basically blow up one of these canisters, the mustard would kind of all just sink down into the trench. So it was terrible, like just horrible stuff. Here you have some images of mustard exposures that are a little more recent. On the left, you have the foot of a child that was swimming in the Baltic Sea. I don't know if any of you know where the Baltic Sea is, but it's kind of that sea that's in between Sweden and Finland over there and Russia, the Baltic Sea. You got countries like Poland and Germany, Denmark that have coastlines on the Baltic Sea. So why would this kid swimming in the Baltic Sea get exposed to sulfur mustard? The answer is that after World War II, a lot of sulfur mustard was dumped into the Baltic Sea, and those canisters have started to leak and break and release this stuff. And so it's a big problem. In fact, the United States had a disaster in 1943. This is now World War II in a city in Italy called Bari. I don't know if you know where Bari is, but it's on the east coast of Italy. It's about halfway down on the Adriatic Sea. And the U.S. had warships stationed in the port of Bari. Those warships were supposedly free of any kind of weapons, but there was a disaster in 1943 where canisters of what we now know is mustard gas were released into the sea, into the environment. There was over 600 soldiers who were injured. And so while we didn't actually use chemical warfare agents to fight World War II, we had them ready in case, I guess, someone else was going to use them first. And so in the 1930s, going back a few years, the United States Army developed nitrogen mustards. Nitrogen mustards were then later discovered to have medical properties and that they could be used to treat leukemia in patients. So in fact, the very first chemotherapy drug that was developed was a derivative of mustard gas called mechlorethamine. It's a type of nitrogen mustard, and it was first used in 1946, right after World War II. You know, the whole thing is linked to Bari. I don't know if I'm running out of time here, but there were medical scientists who treated the casualties of the Bari disaster, and they found that these guys their white blood cell counts dropped significantly. And later, these two guys, their names were Goodman and Gilman. They're highlighted here in yellow, Goodman and Gilman. These guys, they were medical researchers in the Army during the World War II. They got drafted. They had to serve all of that. But when the war was over, they went to Yale University, became doctors, physicians, and they remembered that the sulfur mustard had depleted the white blood cells in the soldiers. Now, this whole Bari thing, by the way, was covered up by the government. It took 50 years before it became declassified. Most people didn't know this. But Goodman and Gilman decided to try mustard as a chemotherapy drug against people with leukemia because of what they remembered from their time and serving in the Army and what the mustard did to the white blood cell counts of the soldiers who got exposed. So it's kind of an interesting story. So here you have this like terrible chemical warfare agent that at certain doses and at the right condition can be a useful drug. And so other nitrogen mustards have been developed since then. Probably cyclophosphamide is the most commonly encountered one today. There's another one called bendamustine. This is the compound chlorothamine that I put a box around. It's called HN2. So the U.S. Army, they developed these nitrogen mustards. They called them HN1, HN2, HN3 to distinguish them from Ph.D. But HN2 was, of all of these, was kind of the least toxic and was the one that translated into the first chemotherapy drug to treat leukemia in the late 1940s. Okay, so I'm going to maybe speed it up a little bit, just to show you what I actually do in my lab. Of course, I can answer any questions in a little while, but let me show you what we do. So we use a mouse. You can see the mouse in the upper left portion of the slide. And we anesthetize the mouse. You see it in the upper right slide. It's under anesthesia. And we apply mustard to the ear. Now, we don't use sulfur mustard because you would need like a government license to do that and a special safety facility. We use nitrogen mustard, the one that was used as a chemotherapy drug. But what's interesting about nitrogen mustard is that it can also cause blisters, just like sulfur mustard. So if you just apply it to the top of your skin, it will cause your skin to have blisters. But if you inject it into a patient intravenously to kill their leukemia, it will kill their leukemia. So this is a drug, it's like context dependent. It can have medical use if you inject it. It can have toxic effect if you put it on the skin topically. So if you look in the upper right panel where the little red arrow is going, we'll apply a little bit of the drug to the ear, and then we let the mouse recover. Eventually, after a certain amount of time, we euthanize the mouse, lower left chamber, and then we do a biopsy punch, lower right chamber, lower right slide. Okay, and that biopsy punch looks something like this. You see in the upper left, that's an 8 millimeter biopsy punch. It's obviously enlarged in this picture, but you can see the little blisters on the ear. They look like little red specks. And what we do then is we fix the tissue. We put it into formalin. It preserves it from degrading. And then we take that formalin-fixed tissue and we embed it into a paraffin block. This is sometimes called tissue embedding. And this is exactly what happens when people go for biopsy punches to see if they have cancer. The tissue gets taken, it gets fixed, it gets embedded into a paraffin block. And if you now look in the upper left, you'll see like a little purple thing, a little purple plastic rectangle. And at the middle of that, you see like a waxy looking thing. And you see my student there kind of lifting up the wax ribbon. And within that ribbon, you see there's a handle there on the right, and the student will turn that handle like a deli slicer. And that blade right there will cut the tissue very thinly. And if you look now in the upper right, you can see those paraffin sections put onto glass slides. And then we go through a staining process, lower left, where we can actually stain the tissue, because normally tissue is what we call translucent and you can't really see it under the microscope unless you somehow stain it. So we do something called hematoxylin and eosin stain, H&E stain, and we mount it on the slide, and then we look at it under the microscope. And when you do that, it looks something like this. So this is the mouse ear. This is a mouse ear that's been treated with mustard. It's very swollen. You can see here on the upper right corner, like a hair sticking out, right? And at the very base of that hair, you have the root, and that's called the hair follicle. Right around it, you have something called the sebaceous gland that produces a little tiny bit of oil that gets onto that hair, right? Adjacent to that, the outermost layer of cells you see is called the epidermis, right? And since this is an ear punch, you punch the ear, you have an inner surface and an outer surface. So you have two epidermal layers here. If you look all the way to the left, to the southeast, you see the epidermis, and instead of seeing the dark stained nuclei, you see the nuclei are white, which means that the mustard has broken all the DNA in there, right? So anyway, what we do is we do this kind of analysis. And just to show you maybe the most obvious change, if you look at the right, you have a mouse ear, and you have your two epidermises. Oh, by the way, you see that thing that looks like bubbles? Like those open big circles in the middle that look like bubbles, maybe? What do you think that is? That's called cartilage. That's called cartilage. And right under that, you see something there. It's like I don't know. It's like banana shaped maybe, and it's got lots of little red things in there. You see those lots of little red things? What do you think those little red things are? Those are red blood cells, right? And if you look a little closer, you see every now and then a dark one, a little dark one there, purple stained cell within the blood cells. Those are the white blood cells. Red blood cells don't contain a nucleus, okay? So the purple stain stains the nucleus. And that's a big fat blood vessel right there that, supplies the ear with oxygen. Anyway, you look at that, that's the negative control. That's an untreated tissue. Now look to the left. Oh my goodness, the epidermis has detached from the underlying dermis, and that's a huge blister, right, that we can see in the mouse ear. So that's kind of what we do. We try to study drugs that can prevent blisters, reduce blisters, trying to find new therapeutics or what we call countermeasures to vesicants. Here's another approach we use. The left panel is just an untreated tissue. The red now stains the nucleus. It's called propydium iodide. It stains the nucleus. The right now is a mustard-treated tissue, and the green indicates anywhere you see DNA breaks. And so when we treat the ear with mustard, we get tons of DNA breaks. That's one of its mechanisms. It breaks DNA. So all that green stuff you see on the epidermis, look at that. It's like everything is breaking and shattering into pieces. And so we're now trying to use this mouse model to kind of understand what happens during blistering so that we can devise a true antidote that can reverse the damage. Now, I know I'm getting to the end. If you look at this slide here, you have a cartoon. The left panel, if you look, the left panel says mouse skin. The right panel says human skin. And I mean, there's one huge difference, right? One huge difference is mouse skin has a lot more hair, right? Mouse, in fact, has fur, right? It's very furry. But another difference is that the human skin has a huge epidermis. It's much thicker, right? If you look under human skin on the right panel, you see this multi-layered epidermis. And on the left, in the mouse, it's really only 1 or 2 or 3 cells thick. So basically, the mouse skin, it's not a great model for human skin. It doesn't actually work exactly the same way as human skin. But we use it in my lab because it allows us to look at inflammation, right? After chemical exposure, we can see tissue swelling, we can see immune cells. If you look a little bit deeper into these images from the epidermis and you head down, you see the blood vessel. And above the blood vessel, you see things like mast cells, right? People with asthma, you know what mast cells are, right? Mast cells release histamine. They can trigger bronchoconstriction and, you know, nasty things. But in the skin, mast cells can trigger swelling. So a chemical could penetrate the epidermis, activate the mast cell degranulates, and you get big swelling of the tissue, like what we see in some of those micrographs I showed you. So anyway, what do? I use a mouse to study mustards. And what am I telling you? It's not the best model to use. But what am I going to do? I'm going to go around and expose people to mustards and biopsy their skin. It's not easy to do. In fact, it probably would be unethical. Not that being unethical is funny. I didn't mean it like that. But, you know, even just to get permission to work with mice, you have to apply to the university. There's a whole committee. There's like people that read this application and decide if your research is worth the pain that the animals have to experience in order to advance the knowledge. So there's a lot of stuff that goes into this. So there are so many people I've worked with over the years. All of them on the left there are either, you know, recent or former students or current students. All of them on the right are people who I collaborate with. This is a picture of Benedette, Hemant, and Savita. They've done a lot of work with the mouse model. This is my lab from last summer. We did a lot of fun stuff working with the blister model and trying to understand you know, why does the epidermis separate when mustard hits it? You know, it's not very clear. We're working on that. All right, so I've told you a little bit about how you get to this place. I just wanted to let you know that since some of you are going to be thinking about colleges, we have a toxicology program at St. John's. We have a Bachelor of Science degree. And if you ever want any information about it, you can just ask Mr. Charleglio to get in touch with me, or you could just jot down my email later, and I'll certainly do what I can to give you some information. I think toxicology is a great major. There's not too many toxicology bachelor's degrees in the U.S. There's probably only like 10 or 15 colleges around the whole U.S. that has it as an undergrad major. We have other majors. Obviously, we have the PharmD degree in the College of Pharmacy and Health Sciences. That's the pharmacy degree. It's a 6-year Doctor of Pharmacy. You come in as a freshman. You leave 6 years later as a PharmD. We have the bachelor's degree in biomedical sciences. We have a master's degree in physician assistant. So maybe you want to be a doctor, but you don't want all the stress. You don't want all the liability. You don't want to get sued. You don't want to pay $200,000 a year liability insurance. You get your physician assistant degree. You can counsel patients. You can work with patients with diabetes, with high blood pressure, with chronic diseases, with cancer. You can have all of the fun with less of the liability. Of course, not as much money, but still a very satisfying, rewarding career. But that's a master's degree now. It used to be a bachelor's, but it's a master's degree. We have the master's in public health. We have the master's in toxicology. We have the Ph.D. in pharmaceutical sciences. And obviously, I'm biased for St. John's. I think it's a great place to spend time. I'm here 18 years already, and I've really been able to grow as a scientist and in my knowledge. But whatever program you're interested in, just look around to read their web pages, get some ideas, contact the emails that they have there, you know, gather your information, try to make a good informed decision. Remember, you're competing not just against the people in your class, but I mean, you know, let me show you this. You see this picture? The guy on the left, he's from China. He's a surgeon in China, you know, like he does surgeries. He wants to get his PhD. He's competing against people like us. The guy here, the second from the left, he's from India. The third one from the left, she's from China. And then these two are undergrad students, and then there's me. But the point is, like, we all want to increase knowledge. We want science to go forward. But it's not just us anymore. We're competing against everybody. Like, there are 18-year-olds sitting in desks in Canada that want the job that you want. There are 18-year-olds sitting behind the desk in England and in China and in India, and they want the jobs that you want. So what are you going to do to give yourself an advantage? Maybe you're going to volunteer to work for somebody. Maybe you're going to learn something new. Maybe you can go work for a lawyer. Maybe you're going to go work for a doctor. Maybe you're going to interested in optometry. Maybe you're going to go work in a pharmacy. I don't know, a part-time job. But do something, because it's getting more competitive. And robots are like eventually going to take away a lot of the jobs. So understand programming, give yourself an advantage. Think about, what's coming down the road 20 years from now. Am I still going to have a job? Am I going to be able to provide? Not that I'm adding stress or anxiety. It should be a kind of a fun thing, because if you kind of think about these things and kind of head in the direction of your interests, you might actually really excel and do something wonderful. And that's what my hope would be for all students, regardless of where they're from. But just, don't be passive about it, because the rest of the world wants to be where you are. Okay, anyway, enough with the lecturing. Special thanks to Morris Catholic High School, and of course to Dr. Chris Charleglio for inviting me to speak to you tonight. I know I've gone over. It's so late. Oh my gosh. But I'll stay as long as you need to answer any questions you have. Thank you.
Thank you. Thanks. Unfortunately, there's no way to clap on this thing, which is something we deal with every week. But everyone's sort of doing the death clap, I guess. That's what we probably should do. I have a million questions, but any of you guys want to start? Any questions? I also want to add, so Dr. Billack also ran for Congress at one point. I don't know if that's fair game to talk about, but that's pretty cool.
Yeah, well, it's part of my life. What can I do? I can't erase it. But I did learn that politics is not for the meek. It's not for the meek. But I did learn also that if there's something you strongly believe in, I mean, I have no nothing to hide. I'm very strongly pro-life, and I've been certainly stressed out about lots of things that have happened over the years, and I just finally tried to make a statement, and I don't regret doing it, but it did cost me a lot of time and effort, and I guess what's the word, frustration, and but I tried. I got off the bench and I tried, and it was valuable. It made me, I think, a more humble person. So I needed that.
I just want to point out there are a couple of adults here. So from my faculty, I have Harmony Lift. She is the environmental science marine teacher here. I see Amy Bauer is here, and she does director of enrollment at Morris Catholic and everything else. And then I believe Dr. Kerr is here, or she was at some point. And hi, Miss Billack. She's there as well. That's hello. So questions for people, from people. What do you got?
I have a question for you.
RC first.
I beat you guys to it.
No, RC first. I'm trumping you.
Did you always have the interest in toxicology, or did that more so come from the exposure to research under during your time Richmond?
Oh, great question. I think it came just from being exposed at Richmond. I kind of went to college. I knew I was smart. I don't mean to sound egotistical. I knew, I kind of thought I was going to major in business, but I couldn't just declare my major when I got there, and I had to take some other classes. And I was just I had a chemistry class with this other professor, Professor Myers, and I mean, oh my Lord, he loved what he did. It was contagious. You just sat there and listened to him, and I was like, I want to be like him, And it eventually led me to Dr. Kinsley's lab. So I think that's where it started.
Miss Liff.
I was just curious about the toxicology lab you worked at Rutgers, who you happened to work with. I also, as a lab tech in my pre-graduate years, worked in the toxicology labs over there.
Oh, really? Oh,
yeah.
That's fantastic. I was there from 1995 until 2001. And I worked for a guy named Jeffrey Laskin, Professor Jeffrey Laskin, in the EOHSI building.
So I was after you. I was in 2006, 2007 with Joanna Berger and her
Oh
toxicology.
yes, yeah. Oh wait,
department.
her husband was like Dr. Gotchfeld.
Yep.
Yeah, he was like so cool. They were both so cool. Yes.
Yep. Cool.
Amazing. Small world.
Yeah.
Other questions?
Does any of your research focus on like actively developing treatment to the damage from like the mustard exposure,
That's
or
excellent.
just like
question.
analysis?
We do study what I call countermeasures. We try to test different countermeasures. So I have a colleague who is an organic synthesis chemist, and he sends us different compounds and we screen them, but we don't screen them right away on the mouse because, you know, it's a lot of work. So we actually have a skin cell culture, and we apply mustard to the skin cells. We watch them die. And then we try to use our drugs, our new test compounds, to see if any of them protect against death. And then we move them up into the mouse model. So a few years ago, we published a paper on a compound, which is kind of interesting, called Epsilon. It's an organoselenium compound that seems to do lots of different things, but when you use it topically, it seems to protect the skin against injury by mustards. So a few years ago now, we got a grant to study it more, and we're in the middle of that now. So definitely, yes, we're trying to find countermeasures that would be useful.
I was actually going to ask what your funding mechanisms were, and if you had any recommendations for them as prospective researchers and as undergrads in a lab, if there were anything that you would recommend for them to get funding.
Sure. Well, first of all, St. John's is very generous to the faculty, so we get a budget. It's about $450 a week, which might sound like a lot or not a lot, but it's really not that much, but it adds up. And so there were many years I didn't have a grant at all, but I was able to publish and do research. For students who are in high school and early stage college, I would say try to identify somebody in an area that's of interest to you. If it's economics, if it's biotechnology, if it's pharmacology, if it's 3D printing, you know, whatever it is, and just offer your services. I'm willing to learn. I'm willing to volunteer, but just keep your word. So if you say you're going to come 6 hours a week, make sure you come 6 hours a week, because if you end up being the one who always calls and says, I can't make it today because, eventually that professor might lose interest. But I'd say most professors are looking for people who are excited about what they study, and they want to share that with them, you know, because you know, there are other options for PhDs in industry and in government, and we kind of come into academia because there's a fun component. It's fun, and we want to share the love. You know, we want to get people inspired and get them thinking about things. So, look, you only got a certain amount of time. You know, we don't know how much it is, but there's an expiration date on everybody, and when it's done, you want to look back and say, man, I left it all on the court. I have nothing to regret. So that's my motto. Just leave it all on the court. There used to be a guy who played for the Knicks. You're probably all too young to remember, but his name was Charles Oakley. You could Google him, Charles Oakley. He was the rebound master. He was before Dennis Rodman. He just got rebounds. Like, he would just get the rebounds and throw it back out, and then the Knicks would score. And there was no shot he wouldn't go after. And so that's my advice. Just go after everything that's of interest to you. You only need one thing to stick, right? That's it. And you can make a career out of it. So anyway, sorry. I do this a lot, you know. The worst thing to do is ask a professor to talk about themselves. You know, they'll just talk about it. You know.
I try to tell them it is hard to describe the feeling of knowing something that no one else has ever known in history, right? When you make that little discovery and it's in the middle of the night.
Yeah, I
I
know.
I don't think we can possibly instill in them that feeling until they do it themselves.
Yeah, it's amazing. I remember I was having a hard time at Rutgers, you know, because I had some early success and then nothing worked. And I remember like thinking maybe I should just quit, you know, maybe it's not for me. And there I was, and I was trying a new experiment, and I couldn't believe it worked. I was just so jaded from having so much stuff not work that I didn't even believe it. But there's this method we do called Western blot, where you kind of separate proteins out and transfer them to this little membrane, and you pour this stuff on it, and it'll glow if the protein's there. And I poured this stuff on the blot. It was like a Saturday afternoon, like, you know, my friends were moving on with their lives and having jobs and buying their house and getting married and everything. And there I was, and the thing was glowing, and I was like, oh, just what Dr. Charleglio says. I can't believe it. This is like, I can't wait to tell this to my mentor. Of course, he wasn't there that day, but told him on Monday, but it was cool. So I agree.
Another important note was Dr. Billack's description of all the histology with the paraffin sectioning and immunohistochemistry and stuff. That's actually what I'm planning on doing with you guys over the summer. So that's the AMI
awesome.
summer project. If I can figure out how to do it in a cost-efficient manner. I've been thinking about playing with horseradish peroxidase, or something like that. But that's pretty cool.
Well, let's certainly chat about it if you need any guidance on it. We do that all the time. So
yeah, I've only done it. So I've done a lot of it, but only with a cryostat. So I thought it was interesting. You're using the paraffin sectioning, because I think that's what I'm going to have to use here. It's a high school.
Well, we could probably give you some blocks as long as St. John's. As long as St. John's is okay with it. I can't see why they wouldn't be. So
yeah, that'd be cool. And I gotta just figure out what we want to look at and how to get maybe do you sacrifice mice on a regular basis just because they don't have the genetic makeup you need, or euthanize just for the heck of it? Is there any way we can get...
I mean, animal research is very regulated, and so you have to justify every mouse you use. But we have a lot of tissues because we feel bad about throwing out tissues.
Sure.
So we collect lots of tissues that we have in blocks because, we figure maybe one day we could reuse them. Because if you fix the tissue in a certain way, you can use it indefinitely. You can use it 5 years, 10 years later. It's still
I have slides of brain slices that I've Nissl stained, and
oh, cool.
I was making for the Allen Brain Atlas. I was making a map with them.
That's amazing.
Yeah.
Go for it, everybody. Take advantage of having these resources because even if you don't go into science, let's just look at COVID, right? It's all they talk about is science all the time. So even if you don't go into science, you'll at least have a different perspective. You'll understand. Maybe you won't be as fearful. Maybe you'll help other people stay calm. It's good.
Real quick teachable moment right there. All of you kids who are watching the interaction between Dr. Billack and Dr. Char, with their networking and their discussion of everything, and we're all just kind of like sitting back watching. That's what you're trying to aspire to, that form of networking where you can actually share ideas off of each other. So Dr. Char was able to form an idea from Dr. Billack in solving a problem that Dr. Char has been trying to deal with for the summer intensive, right? Just so happened.
Well, it's pretty late, so I don't really want to hold anybody much later. If anybody has any other pressing questions, otherwise I'm gonna thank Dr. Billack for swinging by. Maybe we'll try to get him on campus if that's possible later on. And anybody? Nobody else? Okay. Well, thank you very much. That's great. And it's good to hear that somebody in your position says some of the same things that I tell them, that I'm not sure if they believe me, because I'm a high school teacher. So, so they're like, is it real or not? And then they hear it from somebody like you. So hopefully it'll sink in.
Yeah, well, from what I can tell you, you guys got a very good support network, and take advantage of it, because it'll help you in ways you might not even know yet. So thank you for having me. It's always a pleasure to get to talk about my research, and I wish you all the best. And if you have any St. John's questions moving forward, just ask Dr. Ciarleglio for my email, and I'll be happy to help you if I can.
All right. Well, thank you very much. That was really good. So I'll be the one clapping.
Thank you. Good luck, everybody. I hope to hear
right.
good things in the future.
All right. Thanks.
All right.
Bye, everybody.